Hi folks! The following video is going to talk about 3 types of alkene reactions that all show what is known as anti-stereochemistry: halogenation, halohydrin formation, and anti-dihydroxylation. Halogenation is the addition of a halogen, either chlorine or bromine, across an alkene. In the halogenation, each carbon of the alkene gets a new bond to a halogen, and the pi bond is broken. Sometimes the textbook will show this reaction being performed in CH2Cl2 solvent. This is known as dichloromethane, and it is non-nucleophilic, meaning it will not participate in the reaction. The stereochemical outcome of halogenation is that anti-addition occurs. The halogens add to opposite faces of the pi bond. An example where you can see this stereochemistry is in the following cyclic alkene addition reaction. I'm treating this alkene with Br2 in the non-nucleophilic dichloromethane solvent and 2 stereoisomers of product form. To show the anti-addition has taken place, each molecule of product has one bromine added as a wedge and the other bromine added as a dash. In the other case, it's just that the dash is higher up the page and the wedge is further down it. These 2 products are enantiomers. They are non-superimposable mirror images of each other. So I could describe this product mixture as racemic. In the halogenation mechanism, the halogen is going to come in close proximity to the alkene, and it will become polarized. Think about the alkene as having 2 electrons in the pi bond that are above and below the plane of the page. This is the electron-rich site of the alkene molecule. The bromine that approaches closer to the alkene gets a partial positive charge that's getting attracted to the partial negative charge of the pi bond, and then the further away halogen gets a partial negative charge. The first step of the halogenation mechanism has 3 curved arrows. I take the electrons from the pi bond and bring them to the closer bromine, break the bromine-bromine bond and bring those electrons to the distant bromine, and take a bromine lone pair from the close bromine and bring it down to carbon. The effect of this step is that the pi bond has broken and is replaced by carbon-bromine bonds to a single bromine, meaning that there's a 3-membered ring with a bromine with 2 bonds. This bromine is positively charged, and the distant bromine was lost as Br-. This cyclic 3-membered ring structure is known as a halonium ion. The halonium ion is an electrophile, and it can be attacked by the nucleophilic bromide that was generated in the first step. Although it is the halogen that's shown with the positive formal charge, it is the carbons of the halonium ion that will act as our electrophile. I'm going to have an SN2 type substitution reaction at one of the carbons of the 3-membered ring. I'll take a lone pair from the nucleophilic bromide and bring it to carbon, and at the same time I will break the carbon-bromine bond and bring those electrons to bromine. This step forms a new carbon-bromine bond, in this case because I attacked the carbon of the ring on the right. This new carbon-bromine bond on the right is new, and the bromine that was in the middle of the molecule retained its bond to the carbon on the left. So that is this bond in the product. Notice that one of the bromines added to the top and the other bromine added to the bottom. This indicates that anti-addition has taken place. You can think about the bromine of the halonium ion as blocking the whole top part of the molecule, which forces the bromine nucleophile to come in from below. The stereochemistry of the alkene, like whether it's cis, trans, E, or Z, makes a difference in the products of the halogenation reaction. So let's consider the following cis disubstituted alkene being treated with bromine. This reaction would form two different products that are enantiomers of each other. In both cases, anti-addition has taken place, so one bromine that's added as a wedge and the other one is a dash, and the other product just has those positions for dash and wedge switched, but anti-addition has still occurred. Now instead, let's consider a trans disubstituted alkene, in this case being treated with chlorine. Rather than a mixture of enantiomers, this reaction forms only a single product. Anti-addition has still taken place, meaning one chlorine added as a wedge and the other one added from below as a dash, but a second product didn't form. And we have to look at the symmetry of this molecule to make sense of this. Let's imagine rotating the right half of this molecule. This molecule, which contains two chiral centers, also has a plane of symmetry, meaning it's a meso compound. Because meso compounds are achiral, they cannot have enantiomers, so this is the only product formed. A variation on the halogenation reaction is known as Halohydrin formation. This is treating an alkene with a halogen, either chlorine or bromine, but instead of doing this in a non-nucleophilic solvent like before, now you're imagining performing this reaction in a nucleophilic solvent. Instead of adding two halogens to the molecule, you'll add one halogen and a nucleophile, the solvent, to the other position, after it's lost a hydrogen. Here as well, in halohydrin formation, anti-addition occurs. So I use one wedge and one dash in each of my structures to indicate that the groups added from opposite faces of the alkene. Some examples of common nucleophilic solvents that you could see here are water or other alcohols. The first step of the mechanism is the same as that for halogenation. I'm going to have three curved arrows to show the formation of the halonium ion in a single step. I take a pi bond to the close halogen. I break the halogen-halogen bond and bring the electrons to the distant halogen, and take a lone pair from the nearby halogen and bring it down to one of the carbons of the alkene. This first step of the mechanism forms a halide anion and the halonium ion, the cyclic three-membered ring with a cationic halogen. Here is where our reaction will start to differ in terms of what group adds to the electrophile. Imagine that you have a lot of nucleophilic solvent around relative to the amount of bromide anion you have. The highest concentration nucleophile is most likely to attack the electrophile. So instead of bringing in the bromide anion, I will bring in the nucleophilic solvent. I'll take the lone pair from the nucleophilic solvent and bring it to one of the electrophilic carbons of the halonium ion, and I will break that carbon's bond to the halogen and bring the electrons to the halogen. This is my nucleophilic attack and loss of leaving group step. There is a new carbon nucleophile bond. The halogen is now only connected to the other carbon that was formerly a part of the alkene, and the nucleophile, if it started out neutral, it is now cationic, and it still has a hydrogen attached to it. The final step of the mechanism is going to be a proton transfer. I'm going to bring in another nucleophilic solvent molecule, and it is going to behave as a base. I would bring in a lone pair to the proton, break the hydrogen nucleophile bond, and bring the electrons to the nucleophile. This forms the final product, where we've broken the pi bond, one carbon has a halogen added to it, and the other carbon has the nucleophile minus a proton added to it. If the halonium ion formed with the halogen on the top face of the molecule, the nucleophile had to come in from below, meaning that you would have anti-addition, one group added from above and the other one added from below. Let's consider two examples of halohydrin formation reactions. In both of these, I'll use bromine as the halogen and water as the nucleophilic solvent. The only difference is in the stereochemistry of the alkene, if it is cis or trans. For all products that I draw, I need to indicate that anti-addition has occurred if I form new chiral centers. In the first case, to show that anti-addition has occurred, I would keep my carbon skeleton the same shape in the products. In one molecule, the bromine could be a wedge, and the OH group, this is water minus a proton, is drawn as a dash. And in the other stereoisomer of product, the bromine is a dash, and the OH group is a wedge. I have the same pattern of one substituent being a wedge and the other one being a dash in my other product, but the shape of my molecule is different in this case. Because I started out with a trans arrangement of carbons in the starting material, I would keep that same zigzag shape in the products as well, and then show the anti-addition with wedges and dashes from there. Both of these examples involved symmetrically substituted alkenes, so each carbon had the same number of other carbon substituents. We now have to worry about what if you had an unsymmetrically substituted alkene, for example, a monosubstituted alkene. Which carbon of the alkene will get the halogen, and which one of them will get the nucleophilic solvent? It turns out that the regioselectivity of this reaction is that the halogen adds to the less substituted carbon, and the nucleophilic solvent adds to the more substituted carbon. In this case, I've only generated one new chiral center, where the OH group added, so I'm only showing stereochemistry at this position. I'm going to draw out the mechanism for this halohydrin formation to account for both of these products, and then I'm going to discuss why this regioselectivity is observed. I'm going to consider two possibilities. The alkene is planar, and for my mechanism, what if I brought in the chlorine molecule from above the alkene, or what if I brought it in from below the alkene? I'll start by drawing the mechanism bringing in the Cl2 molecule from above the alkene, and then I'll redraw it bringing in the Cl2 from below. The first step of the mechanism is the three curved arrows to generate the halonium ion. This forms the halonium ion's three-membered ring, featuring two carbons, both a part of the original alkene, and the chlorine that's added. A chloride leaving group has been formed as well. In the second step of the mechanism, I will bring in the nucleophile and have a loss of leaving group at the same time. I will bring in the nucleophile to the more substituted carbon and break that carbon's bond to chlorine. Because the chlorine was blocking the top half of the molecule, I brought in the nucleophilic water molecule from below. So I'm drawing that new carbon-oxygen bond pointing down the plane of the page, and that carbon has lost its bond to chlorine, and chlorine is only attached to the other carbon of what was originally the alkene. The water group's oxygen is now cationic. To get to the neutral final product, I will have a proton transfer step. I'll use another water solvent molecule as a base to deprotonate the cationic oxygen. This would form a molecule of H3O+, and I would have my neutral halohydrin product. Now let's consider this whole mechanism bringing in the chlorine molecule from below the alkene. I would have the three curved arrows for the first step of the mechanism. Here as well, I form the halonium ion's three-membered ring with a cationic chlorine and a chloride anion. Because I brought in Cl2 from below the alkene, I draw the new carbon-chlorine bonds pointed down the page. The halonium ion is an electrophile, and there is a lot of nucleophilic water solvent around. I will have my nucleophilic attack at the more substituted carbon of the halonium ring, and break that carbon's bond to chlorine. The chlorine is pointing down the page, so the new carbon-oxygen bond points up the page to show my anti-addition, and now the chlorine is only attached to the less substituted carbon of what was originally the alkene. To get to a neutral final product, I need to do a final proton transfer. Here as well, I will use water as the base in this proton transfer step. This would generate a different stereoisomer of product. To understand why the nucleophilic solvent attacks the more substituted carbon of the ring, I want to consider the transition state for the nucleophilic attack and loss of leaving group step. I would show this transition state with a dotted line showing the nucleophile coming in and forming a new bond to carbon, and at the same time the carbon-halogen bond is breaking. The nucleophilic solvent oxygen, the carbon that it's getting attached to, and the chlorine all have partial positive charges. But it is this carbon partial positive charge that I want you to pay the most attention to. Whichever carbon of the three-membered ring is getting the new bond to the nucleophile is going to get this partial positive charge at the transition state. By bringing in the nucleophile to the more substituted carbon of the three-membered ring, you place partial positive charge at this position. In this case, you're placing partial positive charge on a secondary carbon, whereas if we'd brought in the nucleophile to this other carbon instead, we would be placing partial positive charge on a primary carbon instead. Like carbocations themselves, partial positive charges on carbon are more stable the more substituted the carbon is. So we preferentially form the transition state where we put the partial positive on the most substituted carbon of the three-membered halonium ion. I now want to talk about a different reaction of alkenes known as dihydroxylation. Di stands for 2, and hydroxyl is an OH group. So dihydroxylation is the addition of 2 OH groups to an alkene. For today's video, I'm going to be focusing on what's known as anti-dihydroxylation, where one OH group adds from above the alkene and the other one adds from below the alkene. The reaction steps you need to achieve this outcome come in 2 steps. First, treatment of the alkene with RCO3H. I'll draw out this structure in a minute. And the second step is treatment with an acid catalyst and a nucleophilic solvent, like water. If you use water, you'll end up with 2 OH groups in your final product. In this particular example, after the dihydroxylation, I've generated 2 new chiral centers, so I need to show my products as a pair of enantiomers, where each product has had anti-addition of the 2 OH groups. The method I'll be talking about today for getting this anti-dihydroxylation to occur is treatment of the alkene with a peroxy acid to form an intermediate called an epoxide, and then you open up the epoxide under acidic conditions in what's known as a ring opening step. The peroxy acid contains a carbon-oxygen double bond. The carbon has another carbon group attached to it, and then you have 2 oxygens in a row, and the end oxygen has a hydrogen attached to it. The effect of this reaction step is that the peroxy acid adds this oxygen bonded to the hydrogen to the 2 carbons of the alkene to form a 3-membered ring featuring 2 carbons and an oxygen. This 3-membered ring with a neutral oxygen is known as an epoxide. If I bring in the peroxy acid from above the alkene, I can show the new oxygen with bonds as wedges, or if I brought in the peroxy acid from below the alkene, the oxygen would now be below the carbons, shown as dashes. The second step of the reaction, known as the ring opening stage, treats the epoxide with acid and a nucleophilic solvent, for example, water. This will have the effect of opening up the three-membered ring, adding a hydrogen to the oxygen that was originally in the epoxide, and adding an OH group in the case of a water solvent to generate your dihydroxylated product. It is this step of the reaction that has the anti-addition, where one OH group ends up as a wedge and the other one is a dash. An example of a common peroxy acid you might see in the textbook is this one. It is known as MCPBA. So in the textbook, they could draw out a peroxy acid structure. They might write RCO3H, or they might just write MCPBA. So you should know that MCPBA is a type of peroxy acid. I want to start by talking about the epoxide formation mechanism, this peroxy acid step to form the three-membered ring. I'm going to draw the alkene as viewed from the side, and due to induction, this oxygen of the OH group of the peroxy acid has a partial positive charge. This means that particular oxygen is electrophilic, and it can be attacked by the nucleophilic alkene. This is going to be a complicated mechanism involving 4 arrows in a single step. I bring the electrons from the pi bond to the electrophilic oxygen. I break the oxygen-oxygen bond and use it to form an oxygen-carbon pi bond. I take a carbon-oxygen pi bond and use it to form a new oxygen-hydrogen bond, and I take the electrons from the OH bond and bring those to one of the carbons of the alkene, all at the same time. In this step, both of the carbons of the alkene get attached to the electrophilic oxygen to form a three-membered ring. If the peroxy acid came in from above the alkene, the O would be on the top half of the molecule, or if the peroxy acid approached the flat alkene from below, the oxygen would be pointing down the page instead. The rest of the atoms of the peroxy acid, excluding that red electrophilic oxygen, get lost as a carboxylic acid. Now let's consider the epoxide ring opening mechanism. Imagine treating the cyclic three-membered ring with an acid catalyst in water solvent. This will give the anti-addition to generate the OH substituted product. The first step of the mechanism involves protonation of the epoxide. H3O+ is going to be the acid, and the epoxide oxygen is the base. I would draw the 2 curved arrows of this proton transfer step. The carbon-carbon-oxygen three-membered ring is intact, but now the oxygen has a third bond to a new hydrogen, and now it has a positive charge. Instead of being called an epoxide, this is now called an oxonium ion. Having the oxygen protonated actually has the effect of making the carbons that it's attached to more electrophilic. I'm now going to bring in my nucleophilic water solvent molecule as a nucleophile and have a nucleophilic attack and loss of leaving group in the same step. I will bring in the nucleophilic water molecule to one of the carbons of the three-membered ring and break that carbon's bond to oxygen. Now that that carbon-oxygen bond has broken, the oxygen is only attached to the carbon on the right, and now it is present as a neutral OH group, because the OH group of the oxonium ion was facing up the page that forced the water nucleophile to attack from below. So I draw that new carbon-oxygen bond pointing down the page. Oxygen is cationic here. To get to the neutral dihydroxylated product, I need to deprotonate the cationic oxygen. I can use a water solvent molecule as a base in this proton transfer step. This would get me to that neutral final product. So here I've just drawn the epoxide ring opening mechanism for one of the starting material orientations where the oxygen was facing up the page. If I repeated the mechanism with the oxygen pointing down instead, I could get to the other enantiomer of product. To wrap up today's video, I want to draw your attention to some similarities for cyclic three-membered ring intermediates you've seen so far. We saw this in oxymercuration-demercuration as the mercurinium ion, featuring a carbon-carbon-mercury three-membered ring, where mercury has a positive charge. And in today's video, you saw two examples of cationic three-membered rings, featuring either a cationic halogen in a halonium ion, or a cationic oxygen in an oxonium ion. One similarity in each case is that there is going to be backside nucleophilic attack and loss of leaving group to these intermediates. If the oxygen, halogen, or mercury is blocking the top half of the molecule, the nucleophile is forced to approach from below, giving you that anti-addition product. Another similarity is that there is a lot of flexibility in the type of nucleophile that can attack these intermediates. It could be a halogen, it could be water, an alcohol, or even an amine. As long as it is a nucleophile with a lone pair that can be donated, it could attack the carbon of these cyclic three-membered ring intermediates. And also in all of these cases, when you're under acidic conditions, meaning conditions where you have a cationic intermediate, like shown up above, when you bring in the nucleophile, it will attack the more substituted carbon. Attacking the more substituted carbon of the three-membered ring gives a transition state that places a partial positive charge on a more substituted carbon, meaning that transition state is relatively stable and it has a low barrier. As an example of some similarities for these reactions, I want to imagine 4 different reactions of the same alkene. And it's being reacted under oxymercuration-demercuration conditions, being reacted with a halogen. In this case, you can assume with a non-nucleophilic solvent present, since no solvent is drawn, under conditions where you have a halogen as well as a nucleophilic solvent. And in the last case, these are anti-dihydroxylation conditions. The first set of reagents features a nucleophilic water molecule. There will be a cyclic three-membered ring mercury cation intermediate, and then the nucleophilic water molecule will add to the more substituted carbon of what was originally the alkene. After this reaction, you will have added a hydrogen to the less substituted carbon of the alkene, and an OH group, because I had a water nucleophile, to the more substituted carbon of the alkene. In this particular case, this product is achiral, so I don't need to worry about stereochemistry. In the case of treating the alkene with Br2, I will add a new carbon-bromine bond to each of the carbons of what was formerly the alkene. In this example, this reaction formed 2 new chiral centers. When drawing the products, you should make it clear that anti-addition of the 2 bromines has taken place. You can do this by making sure each carbon that is chiral has 2 bonds that are lines, a wedge, and a dash, and making sure that in each of the products, one bromine is a wedge and the other one is a dash. In the case of the reaction with Br2 in the presence of water, you would form a cyclic three-membered ring with a cationic bromine and then you would bring in the nucleophilic water molecule to the more substituted carbon of the three-membered ring. This would ultimately have the effect of generating a carbon-bromine bond at the less substituted carbon of the alkene, and a carbon-OH bond at the more substituted carbon. This example forms two new chiral centers, so I need to draw two products showing anti-stereochemistry. Here as well, I can do this by drawing the bromine as a wedge and the OH group as a dash, and then switching those wedges and dashes. In the last example, I start by treatment of the alkene with a peroxy acid, but the second step is treatment with an acid catalyst, but instead of water, I'm drawing an alcohol here instead. In this reaction, the first step would generate an epoxide with a carbon-carbon-oxygen group in a three-membered ring. And then in the second step, you would protonate that epoxide and then bring in the nucleophile to the more substituted carbon of the oxonium ion. The net effect is that you would add the OH group, which features the oxygen of the epoxide, at the less substituted carbon, and the nucleophilic solvent minus a proton from a second step adds to the more substituted carbon of the alkene. Here as well, two new chiral centers have been generated, and the reaction here also shows anti-addition stereochemistry. Alright, so today's video focused on three different types of anti-addition reactions. I talked about halogenation, which adds two halogens to an alkene. This occurs when non-nucleophilic solvents are present. A variation of this reaction, known as Halohydrin formation, occurs when you feature a nucleophilic solvent at the same time as your halogen. And I ended by talking about anti-dihydroxylation, which adds two OH groups to an alkene via an epoxide intermediate. That's it for this video. I will see you in class.